Hi, welcome to the webinar. We will start in approximately 3 minutes from now. We'll allow more people to join in. Thank you very much. Hi, welcome to the webinar. Thank you very much for waiting. We are ready to begin. Today, in this week's webinar, we will look at the die mold machining options in 3-axis available with SolidCAM. Last week's webinar was about a complete process where we showed you how to design a product, how to take that product, create the core cavity, sliders, do the mold design, extract the electrodes, take one of the inserts into machining, machine the inserts, then apply a change to your design and see how how the change is propagated throughout the process seamlessly. So that was about the entire process, wherein manufacturing, we only gave you snippets of the manufacturing or the machining process. Today, we are going to dive more deeper into the machining process that is available with SolidCAM for cutting dies and molds in 3-axis. We will also see certain portion of 5-axis later on. Okay, today's agenda, uh, we are going to see SolidCAM's 3D offering for dies and molds. We will have a live calculation or a live demonstration for two parts, the parts that you're seeing on your screen. One is a small mold insert, approximately a size of 180, 135 by about 90. The other one is a large insert, about 400 by 200 by 120. These are the two inserts that we are going to see live. The third one I've already calculated because it's pretty large, and we have a limited time in our webinar, so we can't do everything on the large part. The large part, we will show you how to apply 5-axis strategies for machining dies and molds for those customers who already have a 5-axis machine in house or would like to cut one of their dies or molds using 5-axis machines. So we will also see that, and then finally we will end with a Q&A. The Q&A is also on uh, live, and that means as I explain, if you put some questions on the chat area and if I'm comfortable enough to answer it, I'll answer it online also. So feel free to drop in your questions. In the event I'm unable to answer it, we will respond to you individually by your email answering your question later on. Okay, so let's look at what SolidCAM offers today for 3-axis machining. We have 3 main categories: the high-speed machining category, the iMachining, and high-speed surfacing. So under the high-speed machining category, we have got the generic roughing and generic finishing techniques inside SolidCAM. We also have a new generation roughing and new generation finishing techniques, what we call as the turbo techniques. For machining of small to medium inserts, especially in roughing, we also have 3D iMachining, which is a high performance milling system inside SolidCAM. It's a revolution in machining, and it's a patented technology, patented by SolidCAM, so nobody else has this kind of technology. And the third one is the HSS, or surface machining, surface-based machining of local areas. Also, we are going to see in one of the parts. So in our generic offering, we have got roughing, contour roughing, hatch roughing, hybrid roughing, rest roughing. And in the HSM, you can see on your screen, we have got in the finishing, we have got at least about 10 to 15 different types of finishing strategies that are there inside SolidCAM. This is the generic part. On the turbo side, we have got hatch roughing, contour roughing, and rest roughing, which we are going to see a lot today. Turbo finishing, we have got a very uh, uh, to the point, specific finishing strategies of constant Z rest, linear, constant step over rest finish, pencil machining, and then the combination. Combination strategies are available with both of generic as well as turbo. Uh, I have been in this business of CAM for the last 26 years. I started my career way back in 1994, where, especially in India, the commercial machining shops were not many. I had just handful, while most of them were captive machining shops with large automobile corporations or large white good manufacturers. For the last 26 years, I have worked with various CAM systems, and I've machined molds, I've machined dies, patterns, high pressure die casting dies, several of them. And what I have come to realize is that although your software has got tons of different machining options, in the end, on the practical shop floor, not more than 4 or 5 options are regularly used. And this is coming from my experience of working with several mold makers and die makers. Okay, although you have got several options, it boils down to those 4 and 5 options, how powerful they are, because those are the ones that users or programmers are going to use them in and out every day. So what I've done is, out of this entire list, I have compiled what are the most optimum roughing and finishing operations that generally are used widely by customers. So I have removed those options that generally people don't use. For example, in roughing, in generic roughing, or even in turbo roughing, people use contour roughing and rest roughing. These are the 2 main roughing options that are widely used by users. It could be different softwares. I'm not just saying SolidCAM. It could be different software, but these are the 2 main options in roughing people use. Same goes with turbo, contour, rest. Apart from this, we have hatch roughing, we have rib roughing. I have not seen till now any sizable amount of people using hatch roughing for die molds. It's very rare. Of course, in aerospace, people use it, but that is for a different purpose. And today, we are not talking about aerospace here. In finishing, the most commonly used 95% of the times, the two strategies that are used by mold makers is constant Z and linear. These are the these are the two strategies that are used by mold makers to actually finish their part. The other 5% is taken over by rest finishing and to some extent constant cusp machining. These are the 4 or 5 different strategies generally people talk or people use uh, in their day-to-day life. Okay, it's not that, for example, I've not seen people use radial machining. I've not people used morph machining or even spiral machining, boundary machining. Not all of these options are used in everyday life. They are used, but very rare cases. Most of the times it's constant Z, linear, horizontal for machining the flat areas with bullnose and flattened mills, and apart from that, rest machining. So these are the main options, and today our entire machining is going to focus on these options only. Whereas for others, for I call them as academic interest, we're also going to see the other options, but on purely from an academic point of view. Let's move to our first roughing strategy that we have in SolidCAM, and that's iMachining 3D. iMachining 3D is a revolution in CAM. We had a completely different uh, webinar for this. We had about 700, 800 people attending this webinar where we showed just iMachining, the theory behind it, how it works, and stuff like that. Today, I'm going to be touching on the salient features of iMachining. So it's an amazing technology that regularly saves 70% or more in machining time. And if you're cutting really hard materials with small tools, the savings in cutting or on machine can go up to 90%. Optimized machining, it uses the technology of iMachining 2D coupled with what we call a Z step, and it then can machine the 3D parts or sculptured surface parts like dies and molds. It uses the deep roughing cycle of iMachining 2D first to remove or scoop the majority of material, and the area that is 3D is then built up using the Z step method. Rest machining is also possible using iMachining 3D, where it checks up the dynamic stock remaining, and based on the dynamic stock, it creates only the toolpath into the areas where material is really remaining, and then machines that area. It does intelligent localized machining and optimum ordering. You will not see any retracts coming out from iMachining because it joins from 2 steps using a 3D retract option. So you'll not see anything going to the safety plane and then coming down. A dynamically updated 3D stock model eliminates completely air cutting. And most important thing is a patented product inside iMachining 3D, which is called as the Wizard. It generates the optimum cutting conditions like RPM, speed, feed, depth of cut, sidestep, the style or pattern of cutting. Everything is done automatically based on the machine that you have defined, the material you have defined, the tool you have defined, and the geometry that is presented for machining. So all of these are done automatically by iMachining 3D. And combined with HSM and Turbo HSM, you can actually finish a part. That's what we are going to see today on the small insert where we are going to use iMachining. So that's just about iMachining. Let's move on to our generic HSM. It's a time-tested engine. It's been there for a long time with us, with SolidCAM. Complete control over all the parameters of machining. It has got an amazing toolpath editing function using boundaries, Z levels, or a combination of boundaries and Z levels. You can edit the toolpath in any plane, just not XY. You can edit in YZ, XZ, or any plane as defined by the user. So there is no restriction on from which side you could edit a particular toolpath. The engine is such that it creates very smooth toolpaths and even smoother links. So you'll not see the machine jerking when there is a retract or when it needs to travel from one region to the other, or when it's cutting even a part or a contour inside. It has got comprehensive set of boundary creation tools, very important. We have got a very powerful boundary creation tools inside HSM, the generic HSM, and coupled with SolidWorks sketching functionality, it gives the user great deal of flexibility to create the boundaries the way he wants it. Today, we are also going to touch upon the boundaries and how we can use the boundaries not only to machine HSM, but use the boundaries of HSM to machine something else. Okay, use some other technology to cut the part. Going over to HSM, it has got very powerful roughing and finest finishing toolpaths available for 3D high-speed machining of complex parts, aerospace parts, molds and dies, unique machining and the linking strategies for generating high-speed toolpaths. The cutting moves and retracts are smoothened, and they are maintained to give you continuous smooth machine motion. Retracts are kept down to minimum to minimize air cutting, and the toolpath is both efficient as well as smooth. So this is in short about HSM and iMachining 3D. We'll touch upon Turbo HSM when we can even touch it right now. So Turbo HSR and HSM is a new generation 3-axis machine engine. It has got extremely fast toolpath calculations, lightning fast recalculations because it stores a lot of data and reuses the data when a user wants to recalculate a certain toolpath. It has got true 64-bit architecture, which means it will utilize all the cores available on your computer to create or run a process. So the more number of cores you have, the faster will be the calculation. It has got contour, hatch, and rest roughing patterns for roughing, constant Z, linear, constant step over, including rest finishing options for toolpath and finishing, complete collision checking of your holders, including the part also is available inside SolidCAM's turbo machining. So what we are going to do now is we will move to the presentation when we start calculating the toolpath, because a calculation of toolpath for the small insert can take about 5 to 7 minutes, the complete calculation. And in the meantime, we can finish off more slides explaining to you more in depth about what turbo is all about. Let's go to the software. Okay, so I'm going to open the small insert. Okay, so I have the part here, and you can see the part is 180, 135, and roughly about 88 millimeters, but the actual depth is about 61 millimeters. But it's a small insert, so I would like not to spend a lot of time on just programming this, because it's going to be very easy for me to program inside SolidCAM, even though it's a 3D part. So what I've done here is I have a process that I've stored, and I would like to apply that process onto this and then explain to you each parameter inside the toolpath, and then we'll run the calculations. Okay. So I'll go to the template, and I've got the small mold process here where I have got all the operations here with me, and I'll apply this to this particular part. Okay, no problem. So the process is applied. I'm going to delete the first operation. We are going to recreate that. So what I will do is I will add an iMachining 3D operation here. Like I said, in iMachining 3D, you need to define your machine, you need to define your material, the tool, and the geometry. We have not done yet all of that. We'll just save this. Okay, let's pick the tool and just save it. I'll pick 16 millimeter. It's a 16 corner radius 2 bullnose tool. So I'm going to save this process here. I'm not going to calculate, and I'll reorder this process. I'll take the finishing below the roughing program. So I have my rough here. Let's go and define the two main things that are needed for iMachining. First one is the machine, and the other one is the material. So what I have in my database, I have got several machines. So I'm going to pick, since I'm from India, I'm picking up an Indian machine. I'm picking an AMS MCV 450, which has got 8,000 RPM. Okay, this is a machine that I've defined, and it has got a maximum feed rate of 10 meters. and it has got a spindle power of 11 kilowatt because it's a Siemens based machine. So it's a Siemens 840D based machine, and we have an efficiency of 95%, which means it's a direct spindle. It's not a belt driven or a gear driven spindle. So that's the efficiency. 95% is the efficiency. Let me save it. I'll save and exit. For the material, I'm going to minimize this. And what I've done here is for the material, I've downloaded from Bowler or from Udelholm. I've downloaded what is their material called Impact Supreme. This is a 48 HRC pre-hardened block that can be ordered. And if I go into their sheet or the specs sheet, I have got what is called as the ultimate tensile strength here. Okay, this is the ultimate tensile strength of the material. It's 1020 Newton per mm square. This is what is needed by iMachining. It needs to know the ultimate tensile strength of the material that you're trying to cut. Okay, and then these values will be used by iMachining to perform the operations. So let's go back here. I'll go to the machine database, material database, and in the steel, I can add any steel here. I have got Impact's Bowler here. I have defined the ultimate tensile strength as 1020 Newton per mm square or megapascals. They are the same. And the ISO group here, I've defined it as P steel. Okay, so that's the material that I've defined. I'll save and exit. So what I've picked up is Impact's Bowler with 1020 and AMS MCB 450 with Siemens for machining. So my first two items are defined. So I can go and edit my iMachining 3D toolpath. The next thing I need to define is the tool. So I'm defining a 16 bullnose with a 35 millimeter cut length, a helix angle of 38. The helix angle is very important for iMachining because it calculates the stability of cutting. It tells the user whether you're going to have vibration or chatter or not based on the helix angle and the number of flutes. And it is a 4 flute one. So I'll pick this. And you can see that once I've picked the geometry, the target that to be machined. So I've picked the target to be machined. I've picked the tool, machine, and material. iMachining already has calculated for me the parameters. It says RPM of 2048, feed rate of 1869, maximum step over of 0.5, minimum step over of 0.1, and depth of cut of 31 millimeters, the actual depth of cut. And if I go into the more conditions, I can see that it's only using 0.7 kilowatt from my 11 kilowatt that is available on my spindle. So it's truly underperforming at the moment. Okay, that is because I have not yet utilized what is needed. So what I will do is instead of level 6 or increasing the aggression, I'm going to drop down my aggression to level 4 and then push the turbo button. The moment I push the turbo button, you can see that it now starts to utilize 9.7 kilowatt from the 11 kilowatt spindle. If you ask any machine tool person, this is not a great value because it's almost 90% of the spindle power that is being pulled. An optimum life can only be achieved when you're under 70% of the spindle power. So I need to adjust it. iMachining allows you to override certain conditions. For example, if I want to reduce the power on the spindle, I will reduce the engagement angle. So my current engagement angle is set at 58 degrees by iMachining. I would like to override it and bring it down to 45 degrees. The moment I bring it down, you can see my power requirement also has gone down to 6.5 kilowatt. And based on these cutting conditions, it recalculates again the parameters. So RPM of 5,203, a feed rate of 4.9 meters, a maximum engagement radial of 1.9 millimeter, minimum radial engagement of 0.5. And in my second view, I can see the VC, which is about 262, and the FZ is about 0.15. So this is the cutting conditions that iMachining has decided for me. We'll go into the technology. I'll say keep 0.5 millimeters of offset for me or stock for me for my next operations. And I would like to keep a scallop of 1 millimeter here, not 2 point. I would like to keep a fine scallop. I'll save this. And let me start the calculation. You can see that it utilizes the multi-cores available on my computer. I have got, it's a 6-core system, so I have 12 logical processes here, and the calculation is done. We can look at the simulation. Let's go into Solid Verify. So it takes a full depth of cut and then uses the Z step to create these scallops for me for machining the other area. Okay, so my roughing is done. I can now move ahead and focus on myself on rest roughing and finishing this part. So what I'm going to do now is I'll put several processes together after we do the next finishing. What I want to do now is I would like to finish my parting surfaces because I don't want them to be involved into my rest roughing functionality. I want the parting surfaces completely to be finished. For this, I will use a new generation of finishing techniques that we are releasing in 2021. It's called as a geodesic machining, where the step over is done consistently. It takes a constant step over irrespective of the geometry that it is cutting. So let's quickly run to that. And here I've got two methods of working, either on the model completely or on the surface. I'm going to use a surface functionality, and I'll say new machining, and I'll ask SolidCAM to pick all the surfaces with this particular color. Okay, that's done. Save it. You're going to use morph between two curves functionality, the outer curve and inner curve, but I don't need to define in Geodesic. I don't need to define the outer and inner curve because that will be automatically determined by the software after I've defined the group of surfaces. I'm using a 12 diameter ball nose here. Let's look at the new tool table while we are at this. I'm going to remove this. In the new tool table, it acts basically what you can do is you can create assembly. For example, I can take an adapter of BD40, drop it on the holder, and oops, not BD50, sorry, it's BD40. So I'm going to drop BD40 here, then go into my BT40 arbors, and I can pick a shrink fit arbor of diameter 12. So I'll pick this arbor and I drop it here. So what you can see basically is we created an assembly of the tool, the arbor, and the adapter. Okay, so the new tool table allows you to do that. You can have several adapters lined one behind the other. In the parameters, I'm going to use a side step, a constant step over of 0.5 millimeters. That's all that is needed. I'll save it. Okay, and let's calculate this toolpath. These are the only two toolpaths I would like to calculate in front of you. The other ones, I'm just going to put them for calculation and we are going to see the result. Uh, since this is a very complex calculation that it is doing because the step over has to be constant, it's going to take about 20 seconds or 30 seconds to calculate on this part. Okay, the calculation is done. You can see that it's consistently delivering me the side step that I asked it to deliver. 0.5 millimeter all around. If I run the simulation, sorry, if I run the simulation, this is how it's going to look like. I'll finish the parting surfaces with Geodesic, and then I'll focus myself on doing rest roughing and the finishing operations. Okay, so that's about the parting surface. Okay, right. Once my parting surface is over, I will now focus on the component area rest roughing. So I'm going to use what we have called turbo rest roughing. We are going to see what turbo rest roughing or turbo roughing has to offer. I'll pick the geometry. 0.5 millimeter is the offset. We're using again a 10 ball nose here. And in the process, my depth of cut is 0.3, and the step over is 30% of the diameter, approximately 3 millimeters. And we are using a zigzag cutting using regions. Okay, and let's save this operation. That's not much in this. Like I said, that the amount of parameters that you need to define after you have applied the template is barely 2 or 3. You don't need to define more than that, and we'll calculate this operation. Even here, the roughing or rest roughing calculations on this, which is a stock-based operation, should not take more than 15 to 20 seconds of calculation time. That's done. So I have done the calculation. Let's look at the simulation. We're not going to look at the simulation of all the tool paths, but just few of them. It exactly goes into the area where material is remaining, and it will only machine those areas where material is remaining. You can see that it's now no longer going to go on my parting area because the parting area is already finished. There's no material remaining on the parting area. It's only finishing the areas where bulk stock is remaining. Okay, this is done. My template has got another rest roughing here using another tool, but I don't want to use it. I would like to use a completely different kind of machining here, which is available with us in SolidCAM. What I will do here is I will add under Turbo 3D HSM, we have got an option called as constant Z rest finish. So I'm going to use completely with constant Z, I'm going to machine the areas where material is remaining. So the tool I'm going to select for my cutting using constant Z here is 8 diameter ball nose. Of course, people would be asking where to put your data. The data can be just put here. You can just define what is my VC. The bowler impacts roughly maximum VC available is about 150. So that translates to an RPM of 5,968. And in the FZ, the maximum allowable is about 0.1. So I'm going to use 0.1 here, which gives me a feed rate of 1193. So 1,200 is pretty good. When it is dipping down in Z, I'm just going to use 300. And when it's retracting up, I will use the entire 10,000 that's available to me. If I go into the feed rate, my rapid, I don't want any G00 motion. So I'll say my maximum feed rate available to me, I'm going to take in G1, which is 10,000. Okay. The reference tool here, I'm going to use, I'll pick from the tool library. The earlier tool that I used was a 10 ball nose. You can pick even a 10 bull nose or a 10 flattened mill if you have used that. There is no restriction on the type of tool that you can pick in SolidCAM. I'll expand the rest area by 1 millimeter. So I will go into the other areas more by 1 millimeter. And in the process, my depth of cut is going to be 0.2, detect the flat areas, and the tolerance is 10 microns, okay? In the geometry, I'll give an offset of 0.5 because I would like to keep 0.5 for my finishing. All right, it's done. I'll just save this operation. The best part about the calculation here is the speed at which it calculates. Sorry, let me close this. You can see that this is live calculating in front of you, and it's taken about 8 seconds to calculate the toolpath for me. Okay, now what you're seeing here is that it did enter into the other areas, which I did not want. So I'm going to edit this, and we're going to go into the constraint boundaries and define one boundary for us. Okay, that's the boundary. I'll accept it, say okay, and I'll say tool to be outside by a value of 4 millimeters. I'll say calculate again. My recalculation time is hardly 4 seconds. So I had said that when you recalculate, it's even more faster. So this is how the machining happens. It takes everything in constant Z. It takes the previous tool into account and then cuts the part. Okay, this is done. I'm now ready for my finishing, and my finishing will be done, like I said in my opening statement. Most of the finishings are done using constant Z and linear, so I'm going to use constant Z and linear, but there are certain regions here that will need a different kind of finishing. We are going to see that also. So I will put my first calculation here for constant Z. I'm going to use the 8 diameter tool, the tool that I used for the last rest machining. And the boundary here I'm going to use is this one here. I want it to machine only in this area. I don't want it to go out. Doesn't make any sense. Tangent, depth of cut of 0.3, and the slope angle is, it has to machine between 47 degrees and 90 degrees only. Detect flat areas. Okay, let's save. I'm not going to calculate this. I'll go to my next toolpath, which is the linear. Also pick the target. The tool is the same. Constraint boundaries. I can either pick that, or I can reselect the boundary again, or I can just pick what the earlier toolpath had. And in the passes, we're going to use 0.3 step over with 45 degrees, machining from 0 to 48. So there's going to be an overlap between the two toolpaths, which is needed. And it's a bidirectional cutting. So I'll save this also. Let's focus on calculating these two toolpaths. I'll put them for calculation. So what you're seeing here is it takes both these processes and puts it on separate cores for calculation. So both are running simultaneously. The linear is running simultaneously. The parallel also is running simultaneously. It's finished calculating the linear. It is waiting for constant Z to collate the results and show me the toolpath. That's it. My calculation is between constant Z and linear, both are done. So let's look at the linear machining here. And I can see that it's going into these areas where I would like to apply completely different type of machining. But since it's already machined this area, I don't like this result. So I would like to edit this toolpath and remove those areas which I don't like. So I can apply what we call as the toolpath editing functionality. I'll switch off this toolpath and I'll say, remove the toolpath from these boundaries. So the boundaries I'm going to define, I'll just pick the edge. Okay, that's the first edge. The second edge. The third edge here. And the fourth edge here. Okay, I would like SolidCAM to remove all the toolpath within this boundary and keep the toolpath outside this boundary. So I'll apply. Okay, you can see that it's removed the toolpath from within this boundary and kept only the toolpath outside the boundary. I can now use completely different method of cutting, and we call that as constant step over. So I'm going to apply constant step over machining. And here we are going to look at some boundary creation tools. I'm not going to pick the edge, but I would like SolidCAM to tell me the boundaries of these surfaces using the tool diameter. So I'll pick the target. Let me pick the tool. It's again the 8 diameter. And in the drive boundaries, I'm going to use a function called as selected faces. So I will ask SolidCAM to pick faces of this color and then generate the boundary for machining using the tool. Okay, it's calculated already the boundary. And if I click on show, you can see that the 4 boundaries are already calculated by SolidCAM. Okay, I'm going to use this boundary. And in the passes, okay, sorry. In the constraint boundary also, I'll pick the same boundary. And in the passes, I'm using a step over and step down of 0.2. So it's a constant 3D constant step over. Save this. I'll also go to the next toolpath, which is my rest machining. Pick the boundary, pick the target. I'll pick the tool. I'm using a 4 diameter ball nose here. Constraint boundary, I would like to create the entire one. My previous tool is 8 diameter. It's an 8 ball nose. So it compares the material left out with 8 diameter and then machines only those areas where material is remaining. And I'm using a steep threshold here of 45 degrees. So anything between 0 and 45 it will perform, or it will follow the profile using linear machining. Anything above 45 to up to 90 degrees will be performed using constant Z. So if I go into the link, I can say bidirectional when doing shallow regions and climb machining when you're doing steep regions. So I can have different linking options when you're doing the machining. So let me save it. Let me calculate this toolpath, the first one. Okay, that's done. You can see that it's following the profile, the boundary that we created, and it's machining the area. Okay. Why the toolpath went out? Because we used what we call as a contact point of the tool. That's why the toolpath has gone out. But what you're seeing here is the locus of the tip. The actual contact is like exactly happening at the edge. That's why the tool has gone out. Let's switch off this and calculate the rest machining. Somebody asked if we can have different offsets. Currently, we're using constant offset. Yes, I'll show you in a moment once this calculation is done. We have got something called as a global offset, or we could give radial and axial offset, two different offsets. Let's finish calculating. And that's how my toolpath looks like. I've got areas where it is steep, it's doing constant Z machining. Areas where it's shallow, it's doing a linear machining. So for people who would like to look at the different offsets, okay, let's go into the passes. So you've got floor offset and wall offset. We have got two different offsets. So you could have different one. You can say I want 0.5 here, and I could have 0.2 on the floor. I can have completely different offsets. Okay. The same goes for turbo. I'll show when we are handling turbo how we can have different offsets. Okay, again, in the rest machining, it's gone into this area. I don't like this area, so we can always remove from using the toolpath editing. I can just remove the extra passes from these two regions. Okay, so I'll say accept this, two regions, keep the toolpath outside this boundary, calculate. Okay, this is done. Toolpath removed. And what we can do inside here is we can run another constant step over toolpath. So I'll pick the boundary. This is the boundary I would like to machine inside. And this is the boundary I would like to machine inside. Okay, it's confused. So I'll help it. Okay, so this is the two boundaries I would like to cut. And in the geometry, I'll use a target, just hit the calculate button. Sorry. Contour 4 is my boundary. You can see that we did the entire calculation in roughly 20 minutes. Okay. We can run the simulation. We can do a lot of other things. This calculation is done. We're machining, and this entire part has now been calculated using different techniques. What you've seen here was the technique of constant Z machining, linear machining, and to some extent constant step over. Although we had several other machining techniques, none of them were really useful on these kind of paths. Okay, they have their own specific use, but most of the times this is the one that you're going to use. If you want, you could always generate a G code. What we are going to see here is a Siemens G code coming out. And once the G code is generated, you could also go ahead and generate the tool sheet. We're going to see the tool sheet generation for my next part, which is a much more bigger and a complex part, with more operations. You can see with iMachining, the feed rates are never constant. Why? Because it's generating what we call as a constant cutting load on the tool. The force on the tool is always constant. By varying the radial bite into the material and the feed rate, it generates constant cutting load on the tool, thereby improving the tool life dramatically. We have seen that the tool life with iMachining can go as high as 200 to 300% compared to a conventional tool life that you would get otherwise. And that's one of the reasons why iMachining is so powerful and popular. All right, so we have done with the first part. We'll look a bit again. Let's open the next part and we will look at our uh, presentation, and we'll see what Turbo has to offer. So I have my second part here, and you can see that it's a colorful part. Of course, I did spend some time in identifying and uh, isolating areas that need machining in different ways. So I spent about, let's say, 15-20 minutes in trying to identify which areas need the regular machining, which areas need some special machining, which area needs to be isolated and done differently. So I've just made my segregation, defined them different colors. Why do I have used a different color? It becomes much more easier to uh, pick surfaces based for, let's say, for calculation for boundaries, for calculation of toolpaths. If you are doing surface based machining, it becomes very easy to pick if there are more than 2 or 3 faces. If there are 2 or 3 faces, it doesn't make to it's no use coloring them, because you could just pick them manually. But if there are many surfaces, you color them and it becomes very easy to pick them up. Somebody asked if uh, you use undercut passes to remove, or rather use edit machining or edit toolpath to remove undercut passes. You have to realize that SolidCAM directly has got a function to do undercut machining using constancy. So you can use your slot mill or even a lollipop mill to machine undercuts in 3D. Okay, you don't have to specify where your undercuts are. SolidCAM will find them for you, and it will make sure that it will generate a very safe and efficient toolpath considering the arbor, the shank, and the cutting area when it's doing the undercut machining. All right, let's get back to this part. Let's go to the CAM part directory, 2020. I've got this process here. I'm going to apply this process. Okay. Somebody asked me if I can use colors in my templates. Unfortunately, our templates currently don't store any color, but in the future, you will be able to use that uh, possibility. It's there. It's already in works. So it's work in progress. Okay, so I have got my process defined. I've got a roughing with 32R1.9 high feed bullnose cutter, rest roughing with a 16R1.9, again a high feed bullnose cutter, rest roughing with 10R1, which is a solid carbide bullnose end mill, and then a corner rest finishing with with 8 ball nose, horizontal area finishing, which is absolutely flat, zero, nothing. It doesn't make sense to machine with a ball nose. It's waste of time. We are going to do that with a 10R1 bull nose tool. And then we are going to use a new generation geodesic machining for machining what we call, this is a forging die. So I'm going to machine the gutter with the geodesic machining. The gutter also as a part of the uh, profile we are going to do with geodesic. And then the regular constant Z machining, linear machining, and rest finishing and pencil. This is the entire process. So what I'm going to do is I'm going to first define this entire process, put it for calculation, and then we will go to my presentation. As the calculation runs in the background, we will see the presentation. So the first one is a turbo roughing. So I'll pick the target, and I've kept an offset of 0.7 millimeter. Turbo roughing has got several features, and some of the features are it can recognize stocks with undercut. So let's say you have a part and it has got, or let's imagine a spear. You have got a light region and a shadow region. So you have got a stock that really cannot be machined. But in many softwares, Even if you provide a stock with an undercut, it doesn't recognize an undercut and just generates straight tool paths there. It's useless. It's cutting air because there's really no stock. But when 3-axis softwares look from a particular direction and they don't see anything but straight walls, if there is nothing, then they just see a straight wall. So they go and machine completely. But in Turbo, I can tell to Turbo that this particular stock has an undercut, so it will exactly come and stop where the undercut starts. Beyond that, it will not do any machining. Okay, so that's one of the features that we have in Turbo. Apart from that, you can define fixtures, clamps, and other things. Both, you could define a clamp as a 3D geometry, or you could define a clamp as simple sketch. Both possibilities are given inside Turbo. You can define pre-drilled holes. You've already done the drilling and you want the tool to always go and enter that particular part. That's also possible in Turbo. So I've picked my geometry. My tool is a 32R 1.9 high feed bullnose. Everything else, boundary, I'm not using it because I've defined a stock. It's not necessary to use boundaries if you have already defined a stock. It's not 100% necessary, but if you still want, you can go ahead and define boundaries also. Under passes, I'm going to use a depth of cut of 1.2 millimeters. That's the standard defined depth of cut for this tool. And the step over is 40% of the flat area that corresponds to 11.28 millimeters. Tolerance of 0.1. And in the link, I've got automatic ramping type, so it will choose the ramping based on the geometry and the space available for it to ramp. It could use helical, it could use line, it could use profile, depending on the region, the geometry, and the space available for it for ramping. So let's save this. Okay, let's go to the next, the rest roughing. In the rest roughing, it's nothing but the same one. It's roughing itself. But under stock, I have asked it to respect the stock model. So it's going to see what the previous operation did. And since my earlier operation had only 0.7 millimeters as the offset, I can ask my rest roughing to remove only those areas where material is more than the previous offset. So if my general formula is I use the previous offset plus the tolerance as my next area to be cut, or rest material thicker than value. It's about 0.8. 0.7 was the offset. 0.1 millimeter is the tolerance, so 0.8. So I'm asking SolidCAM to remove material only in those areas where material remaining is more than 0.8. So what it will do is it will not go into areas where there are scallops remaining, because it can happen. Scallops is also a material for it. So I don't want it to go and touch into the areas where scallops are remaining. Just go where volume is there, cut only those areas. The tool I'm using here is a 16R 1.9. Okay, every time I'm asking it to check against the holder, we have got what we call as a dynamic holder collision checking. It checks against the dynamic stock every time, and it keeps a clearance. So this clearance is defined by me. Again, no constraint boundary is needed, but if you want, you can still define a constraint boundary here. Under passes, I'm going to take a step down of 0.5 millimeter and a step over of 40% of the flat area of the tool, not the diameter, but the flat area of the tool that corresponds to about 4.88 millimeters. I'm going to save this. Oops, not selected the geometry. So let's select, save this. Okay. Okay, let's go to the next one, which is again a rest roughing operation of 10R1. I won't spend much time. I'll just pick the target, save. Go to the next operation, which is the corner rest roughing. Again, in here, the geometry, pick the target, constraint boundaries. If you want, we can use it. If you don't want, we need not use it. My reference tool is 12 ball nose that I've used as my reference tool here. I'm going to save this operation also. And the next one is the horizontal area finishing. I don't need to define which are my horizontal areas. SolidCAM will automatically detect them for me. Tool is 10R1 bullnose. Okay, and the step over here is 4 millimeters. So it will find itself which are the ones that are absolutely flat and machine only those areas. So I'll save that. The next very important thing is we would like to cut this pink colored surface, which is in forging terms, they're called as the gutter area. So I would like to cut that. But I'm using the new generation finishing technique called Geodesic, and I'm going to use morph between two curves, which means I need to tell to SolidCAM the outer curve and the inner curve. Now look at that sheer number of surfaces. If I want to pick the surfaces edge by edge, I'm going to spend the next 10 minutes trying to generate the curve. So instead of that, like I told you, we're going to use a trick here. And the trick here is to use a function available inside generic HSM. So I'm going to use a dummy constant Z machining. I'm not going to calculate the program. I'm just going to use that with the same tool. And we'll take the help of HSM to help me define the boundaries. So in the constraint boundaries, I'll say I would like the constraint boundaries of a sill-out boundary. And this sill-out boundary should be created on all these surfaces with this pink color. Okay, so it's picked that surface. I'll apply, say okay. You'll see that very quickly it will generate two boundaries for me. Okay, these are two boundaries. So these two boundaries I'm going to use for my machining. But the trick here is, unfortunately, the boundaries are not they're not interpolable between one operation to the other, because generic high-speed machining is different and my geodesic machining is different. So I can't exchange the boundaries in a straightforward manner. When I can't do that, I can simply go into an operation, open the boundary, and I can ask it to generate a simple SolidWorks sketch. So it will take a boundary, generate the sketch for me. Okay, the sketch is generated. I can see two boundaries here. For me, the HSM work is already done, so I'll delete that operation. That was only used for generating the boundaries. So I'll go back again to my geodesic, edit this toolpath, and instead of using surfaces, I'm using the model. So I'll pick the target, and my first drive curve will be this curve here. Okay, go ahead, go ahead, go ahead. It's made up of several segments because it was a small part. Okay, that's the first curve. Accept. Second curve will be the inner curve. Pick this. So you can see that we use the boundary for HSM, generated the sketch out of this boundary. Now, let's move. Yes, please. And then use the sketch to use this as a boundary for a completely different operation. So this is done, and I'm going to use diameter 8 here and a step over of 0.3 millimeters. So I'm going to save this operation. Oops. Constraint boundary. I'll again have to pick the outer boundary. So I will use this. I already have the curves with me. Oh, I could have used directly the curve here itself. This was contour. So let's go to constraint boundary and it's contour, the outer one. Okay. Let's save this operation and move ahead again. Next one is machining of constant Z of the gray colored profile. So I would like to do the finishing using constant Z machining, and the machining has to happen inside this boundary. Okay, I don't want it to go outside. Within the boundary, all the gray colored area will be machined using constant Z on this target. And the tool I'm using here is again an 8-ball nose. And in passes, 0.3 millimeters is my downstep. Angle range is between 45 degrees and 90 degrees. And it's a bidirectional cutting. So let me save this operation. I'm just saving this operation. I'll put it for calculation, and then we'll move to our presentation to see something else. Next one is my turbo finishing operation. And this time, I would like to machine the locks here. There are two types of locks. One is a purple colored area and the other one is a golden colored area. So I would like to create the boundary, and this time I'm using the seal out boundary option inside Turbo HSM, and I'll pick this surface and I'll say find all the surface of this color, apply, generate the boundary. Okay, we already have the target. So if I click on show, you can see that it's already generated the boundary for me for that particular area. Okay, perfect. Let's save this operation. Let's move to the other area, and here I'm going to use the same method. So I'll generate the seal out boundary using the function here. So let's pick the target, constraint boundaries, say new, select from the model, find the faces, generate, say okay, okay, and you can see my boundary has already been generated for machining that area. Okay, don't need to spend much time. Let's save it. And then I would like to do linear finishing of the area in between the gray colored one. So I'll pick boundary. It automatically picked because it knew that there is a contour one boundary. So it picked the boundary, and it knows that it needs to machine only in between this. Okay, because I'm using an 8 diameter, and the side step here is 0.5 millimeter, and the machining is not at a particular angle, but using optimum angle as decided by the software. The software will find the best possible machining angle for each regions. Because I'm using an angle range of 0.01 to 47 degrees, it's going to find several regions. Each region will be machined using a different angle, which is good for that particular region only. We'll see that in our slide as we go into the PowerPoint. Sorry. Let's save this. Exit. And then what comes up is, since we have finished the gray colored area, we have finished the pink colored area, we have finished the horizontal, what remains is the other 3D area that needs to be machined. Okay. Here I'm again going to use turbo linear, and in the constraint boundaries, I will use what we call as the seal out boundary. And again, here I will pick only those surfaces that are green colored one. That's the reason I have created different colors. Say okay, calculate. And if I click on show, you can see that the boundaries are already calculated for me. I don't need to worry much about it. All I need to do is just save. Again, here we are using the optimum machining angle. Then you have the rest finishing, and then the pencil cutting. And just pencil cutting is just running around after the rest area machining is done. I want to run the same tool around all the corners to make sure the scallops are removed and we get a very good surface finish. So I'll just pick the target here because I don't need to do anything, and I'll save this. Oops. Okay. Let's pick the, save it, done. Right, so we have done everything, and I would now like to put everything for calculation, and then we'll move to our slides. Okay, so I'll pick all the operations, the entire operation, and I'll hit the calculate button. Okay, so as the calculation starts, let's go and look at our slide to see, because all these two parts that we have seen, majority of them have been finished using constant Z and linear machining. Okay, there's nothing more than that, and the rest machining. And to some areas we did constant step over, but there are several other finishing techniques available inside SolidCAM. We also have to look a bit about what turbo machining has to offer. So let's look at the slide, and let's go into the PowerPoint. So like I explained, Turbo HSM and HSR, it's a new generation 3-axis engine, extremely fast toolpath calculations, lightning fast recalculation of the toolpath, true 64-bit architecture. And as I'm speaking to you, I can hear all my computer fans go. Okay, that is because my turbo calculations have started. It's using all the processes available generating a lot of heat, so my fans are on. Minimum definition of parameters, you can see not much parameters that need to be defined. Most are default and they work very well. For roughing, we have contour, hatch, rest roughing, constant Z, linear, constant step over for uh, finishing, complete collision control, including the holders. So if you look at Turbo Rough, we have got, first of all, the main function is that it's a 64-bit calculation, supports all the cores. So for example, my system is a 6-core system, 12 logical processors. Some people have 8 cores, some people have 12 cores. So imagine the speed of calculation will jump up dramatically if you're running the same process on a 12-core machine. The recalculation is much faster because it stores all the parameters that are calculated into the file itself. So if you want to change the step over for it, it's just like a parametric change. That's how quickly it will recalculate back. We saw that in our earlier part. It also has got multiple surface offset selection. Excuse me for a moment. It also has got multiple surface offset. That means I can select different groups of surfaces on the part and provide different offsets. For example, all the horizontal areas that are there on the part, I could say give 0. I want it to be finished in roughing itself. I don't want to spend time doing finishing of that. It happens, many users do it. So it allows you to define different offsets in roughing stage itself. You can create infinite groups with different offsets. Different strategies are available. You can use hatch, you can use contour roughing, which is the offset strategy, and a very powerful rest roughing strategy. The rest roughing is based on either updated stock or previous tool, or a combination of updated stock and previous tool. The user can specify what is the minimum amount of stock it needs to detect to generate a rest roughing toolpath. Below that, those areas will not be touched by SolidCAM. You can have arc fitting, and arc fitting is possible both in the toolpath as well as on the rapid areas. And the rapid area arc fitting provides for a much smoother motions when you're machining on the machine, whereas the toolpath arc fitting allows you to generate much shorter toolpaths. I have had cases where if I don't use arc fitting, I can get a toolpath as long as, let's say, 400,000 points. And the same toolpath, after using arc fitting with the tolerance that has been used for machining, if I use arc fitting, the number of points dramatically drop down to 90,000 points. So it's like almost 25% of the points that were generated earlier. So arc fitting also allows you to use these programs on older generation machines where smoothing codes are not available. So you can use these these toolpaths on older machines, which will also improve your machining quality. Coming to Turbo 3D HSM, we have got, like I said, several methods of finishing in Turbo. One of them is constant Z. You can have adaptive step down, flat area detection, zigzag machining, one-way spiral. You can do a lot of things inside Turbo HSM's constant Z machining. And then we have linear, where I told you that in linear machining, we can have what we call as the optimum machining angle based on the XY plane, based on the part geometry. So if I look further into the same part, you can see that when linear machining does, it changes the direction of cutting based on the geometric location and the shape of that geometry that it is getting. For example, you can see that in just a small area, it has done machining in 3 or 4 different directions based on the geometry. And this is basically done to limit the acceleration and deceleration patterns on the machine. Okay, sometimes going 0 or 90 degrees can actually hurt your acceleration and deceleration. It can come into play very strongly, but by changing the angle slightly, you could limit that influence. So this is one of the most important highlights of linear machining inside SolidCAM's Turbo 3D HSM. And then we have the constant step over. Uh, we have got constant step over, where you can machine it based on the patterns that you get with a consistent step over that you define or the user defines. And there are different ways of ordering the toolpath. You can go from outside to inside, inside to outside, center away, top to bottom, bottom to top, got several options to work with. And then we have in finishing, in the part that is currently being calculated. Once the calculation is done, I'm going to show you also the HSS, which is local area finishing, which is an excellent supplementary module for all our 3D machining. Because there are certain areas, for example, you would like to machine a fillet only. If you have to do that in 3D machining, it's almost a nightmare. You need to make boundaries. You need to make sure that the boundary is the exact size, because if not, it will start going into the other regions. If it is too less, then it will not machine the entire region at all. HSS takes out all that issues. You can machine exact surfaces without defining any kind of boundaries. Okay, one surface or group of hundreds of surfaces can be machined. If there are small undercuts, it can be handled directly by HSS. It uses both Lollipop as well as the slot tools. That's possible. When we go to HSM's 3-axis machining patterns, I explained to you that we have got tons of different machining patterns, but we used only the linear, the constant Z, and to some extent constant step over and rest machining. But there are several other possibilities within the generic HSM of SolidCAM. Some we used, some we did not. Even in constant Z, we have got several methods. For example, on the left side is a classic constant Z machining, where you just define the depth of cut and it just follows the depth of cut by slicing the part at that particular depth and then creating the passes. However, not many people would know that within our generic HSM, we have got an option to apply what we call as a true scallop. You can specify what is a scallop and what is the maximum depth of cut allowable on that particular part. So you can see the same part being done on the right hand side with a scallop of 5 microns. You can see in the areas where there is real 3D, it's applying a 5 micron scallop. But when there is a straight portion, a straight wall, it doesn't need to use that scallop, because even if I take full depth of cut, I still can maintain 5 micron scallop. So here it applies the maximum step over. And as it goes into the next 3D area, again the scallop kicks in. So it will keep changing between scallop and step over based on the geometry that is coming in contact with the tool when it is machining. So this is a very important aspect inside our constant Z in generic 3-axis machining. Apart from the constant Z, we also can apply what we call as a helical pattern, where you have just one entry and one exit, and the tool will wind around the part like as if there's a spring around the part, and it'll just keep going around the part completely till it finishes the part. No retraction between till it completely finishes the part. So this is the helical finishing pattern that we have inside our generic machining. Then we have the horizontal finishing we are going to see in this part, where the software, the generic HSM, automatically will detect all those areas that are absolutely flat and machine only those areas where the geometry is absolutely flat. Automatically, user need not define anything. And then we have the hybrid constant Z machining, where it uses a combination of constant Z machining and the 3D pocketing routine, the 3D roughing pocketing routine. It uses that routine to generate the toolpath, so it can handle horizontal and not so horizontal areas and still machine the part completely, finish the part completely using this routine. And then we have linear. In linear machining, again, we have got a couple of options where automatically, if there are holes in between, the linear machining will take care of that. It will recognize that there's a hole. It won't go inside the hole, but it will assume that the hole was patched up, and it will just traverse over that hole and move further. That's one option. That's one feature. The other feature is when you're doing linear, invariably there will be areas where it will cut very nicely, but there will be walls where the step over will become larger. In such areas, we have got an option to do what we call as a cross machining within the same toolpath. Within the same toolpath, the angle of machining will change, and those areas will be machined exactly perpendicular to the existing hatch pattern. This is done automatically. You just have to pick and say do cross machining. SolidCAM will find where these areas have where the areas have tool paths with step over more than what is required, and those areas it will do cross machining. The next pattern is radial finishing and spiral finishing. So if you have round components and you would like, you can do radial machining and spiral finishing. It's very simple. You just have to specify your start point and the end diameter, and it will machine anything in between using that pattern. No need to define anything else. With just defining a radial finishing point and the diameter of the circle, it will create radial machining passes. The same goes with spiral. Radial is along, spiral is across. And then we have two more patterns, which is morph finishing and offset curve finishing, where we can machine a part using two edges and everything in between them will be morphed out. So the pattern will look, it will start from one edge and it will finish with the shape of the other edge. Whereas the offset curve finishing will take one edge and it will just keep offsetting the passes while machining the geometry inside it. And then we have the rest finishing. The rest machining, it will determine the areas where material remains after machining by a certain tool path, and it will generate uh, passes to machine these areas. Now this can be done in several ways. Automatically you can segregate passes in steep and shallow regions, machining the steep regions in constant Z, machining the shallow regions following the profile. You can use any combination of the tool. Your previous tool could be a bull nose, next tool could be a ball nose, or your previous tool could be a ball nose, next tool could be a bull nose, or it could be bull nose to bull nose to end mill. Any combination of tool can be used for rest finishing. And then we have the 3D constant step over, where you can define a profile, and SolidCAM will start machining parallel to the profile on the entire part by generating a constant step or constant distance between two passes. And these passes of the toolpath are located at a constant distance from each other, measured along the surface of the model. Okay, so that's another finishing pattern. And then you have pencil milling, where it will follow the corners. This is the super finishing, where you can, if you have got scallops remaining on the part, that can be easily removed using pencil milling. And then you have parallel pencil milling, where it will take the same pencil milling and generate multiple passes of that. Instead of going in one pass, it will do several passes depending on how many passes the user has defined. And then you have the 3D corner offset finishing strategy, which is a combination of pencil milling as well as 3D constant step over. The pencil milling will determine the curve, and the curve will be then used for machining using the constant step over. Sorry. And then we have the prismatic part machining. This kind of machining in HSM is designed specially for high-speed finishing of prismatic parts. The strategy actually is a combination of two strategies, constant Z and 3D constant step over. And we integrate these strategies into one smart functionality to do prismatic paths. So if you have paths which have straight walls and floor, you can just give that part, instead of doing 2D machining, you can do a complete 3D machining with bigger step downs and bigger side steps. And then we have the HSM finishing patterns, the combination. You could have a combination of constant Z linear, constant Z constant scallop, and you could create just one single tool path. You can have a different step over for uh, constant Z, you can have a different step over for linear. You can have one-way machining for constant Z, you can have bi-directional machining for linear, but it will combine and give you a single tool path. This is what we call as the combination of finishing strategies. Okay, let's go back to our part and see what has happened. Calculation is done, and let's look at the tool paths. So the first tool path was roughing. Now the best part in SolidCAM is the ability to dynamically view the stock. I'll select the updated stock, And you can see that it immediately shows me the stock remaining after the first operation, is done. So this is how my stock is looking after the first operation. If I drag it to the next operation, it will immediately update it and show me the stock remaining after the next operation. Same, if I drag it to the next operation, it will again run the updation of the stock and show me the stock immediately. Okay, you can see that it's done that stock further. So you can dynamically view the stock. Some users, like power users, would like to see how the stock is remaining and base their next strategy on how the stock is remaining. It's not always that they follow that every time it has to be rest rough. They would like to see how the stock is remaining. You can even take sections across the stock to see how the stock is remaining, and based on that, you can visualize or you can strategize your next cutting strategy. So this particular option is straight away available to users dynamically. You can see the stock straight away on your screen. You can even switch off your design model and you can only keep looking at the stock and nothing else. Okay, let's go back to our part and look at each of these toolpaths. So the first one is roughing, simple. Wherever possible, it's approaching from outside. Where it's not possible, it will ramp. Inside Turbo, sorry, we have got an option to define whether we are using a center cutting tool or not. If you have defined a non-center cutting tool, it will make sure that it will not ramp at all on your part. So wherever areas which need ramping, they will all be skipped. It will not machine that part at all, or that area at all. Next is my rest roughing. You can see efficient rest roughing, not much retracts, machining only in those regions where material is remaining, going only in those regions. This is with a 16R1.9. The next one is with 10R1, the solid carbide bullnose, again going only in those areas where material is remaining. And then I've done constant Z rest finishing. Okay, you can look at that. It's always doing constant Z machining, irrespective of where it is going. It's always doing constant Z machining. So I'm making sure that I'm using the powerful constant Z method and going only in those areas where previous tool did leave material. Once that was done, we have done horizontal area machining. You can see it has picked and found out all the horizontal areas where material was remaining or where it needed to be cut, and we use the bullnose here to machine all these horizontal areas. The areas we detected automatically by SolidCAM. And then comes the best part, the geodesic machining. You can see how geodesic has cut this part. It's followed the outer curve, it's followed the inner curve, but it also has respected the part geometry. So it's not uh, uh, gouging into the part geometry, it's following the part geometry. So it's also done for me another thing. It has machined the exterior part of this gray colored area so that I don't need to touch them again using constant Z. Even if I have to do, I don't need to really touch them. And then I have the constant Z cutting, okay, using the slope angle method. And then the localized machining to machine the locks. Okay, here one, and I've got another lock here. You can see I generated the sill out boundary and it's machining only that area here. And then the linear finishing of the internal profile, only those areas where I asked it to machine. And then the linear finishing of my external parting surfaces. Again, using different methods here. So you can see it's going in 90 degrees here, 90 degrees here, but when it comes here, it's doing at 0 degrees. It's defining based on the surface geometry. Then we have the rest finishing, where it removes the material based on the previous tool and the next tool. And after the rest machining is done, I have the pencil finishing. Okay, just running it everywhere so that we don't have any cusps remaining. But I've got certain areas which still did not finish, and for there, I'm going to quickly run one HSS program just to show the power of high-speed surfacing. So I already have a template here for my high-speed cutting. I'm not going to use the process template, but the toolpath template in 2021. Okay, so the lock top, I'm going to drop it here, say okay. So let me pick the geometry, and my geometry is basically these surfaces on the top that need to be finished, and my edge curve is simply the curve on the top, this one and this one. Okay, this is also done. And in the gout check, I would like to pick certain areas where I don't want it to collide. So in 2021, we can define the gout check now using surfaces or the entire model or a fixture or an STL geometry. Okay, you don't need to have a different a button or icon for that. I'll pick the surface that it needs to check against. So I'll pick these areas and say that please check for collisions with this area. That's it. I'll just hit save and calculate. Calculation is done. And this is how my toolpath looks like. So you can see the power of HSS. Smooth toolpath on a group of surfaces without creating any boundaries. Just pick the surface, just pick the probable gout check areas and calculate the toolpath. Clean, clear toolpath. Okay. Right, what we are also going to see in this, apart from the calculation, is creating our setup sheets. We have got a very powerful tool to create setup sheets, which is either Excel based, Word based, or HTML based. Now, I got an Excel sheet from my customer, and my customer said, please make it exactly like this. He wanted to see during the webinar. So today morning, I sent it to one of my engineers who is an expert at creating setup sheet templates. And within an hour, we had this template ready. And we'll create the setup sheet. He has a particular software at his place, and that software generates the setup sheets in that particular way. And he wanted it exactly looking like that. Yes, please. We can see immediately it created a very nice looking setup sheet for me. Shows me the NC file, the type of machining, what is the tool number, what is the cutter type, what is the diameter, corner radius, what is the length of the tool, what is the holder use, what is the stock step, the Z step, spin, RPM, and stuff like that. Everything is possible. You can create a sheet the way you like it. You have to only send us the template and we'll create the template for you. You send us a sheet or even a photograph of the sheet and we'll create exactly the template like the way you want and send it back to you. So this was about 3-axis machining, and the proof of the pudding is when you look at the parts that were cut. Okay, so I'm going to show you some very nice pictures of the part that were cut, and then we'll quickly in the next 5 to 7 minutes look at the 5-axis options. So this part was done on a Makino PS105 in 240 minutes on a, this was a bowler material, by the way. It's a pre-hardened mold steel 48 HRC. And you can look at the surface quality that was achieved out of, this is pure milling. No hand finishing has been done on this part. Now, this was a high-end machine like a Makino. We talk about an Indian machine, Jyoti VMC 850. The same part was done in 300 minutes, obviously because it doesn't have that kind of high parameters like Makino. But you could look at the surface quality that was generated out of this machining using our HSM and Turbo HSM functionality. Again, this is not touched by hand. This is purely as machined on the machine. The small insert that I showed you, 180, 135, 88, this was also done on a Jyoti VMC 850, cut in 200 minutes. And this is as seen on the machine. You can see still the coolant lying around, no hand touching of this part, the kind of surface quality that you generate. The last part is the one that you just saw. Again, this is as coming out from the machine. This was done on an MCV, AMS MCV 450. This was done in 400 minutes on a pre-hardened mold steel 48 HRC. You can see that the surface quality that comes out from this is excellent. No hand touching is required if you have done the machining in the right way. Right, let's quickly run back to our part, and in the next 7 minutes, we'll have a look at our 5-axis options. Why do we need 5-axis for mold and die? So I have got a pretty large part. It's 860 by 485 by about 120 millimeters. The reason I have already done the toolpath is I knew that we would not have time, and I just wanted to show you the result. First of all, why do we need 5-axis for this? It can be done in 3-axis also. Let's look typically at this area here. Okay, if I measure this area, this is approximately 108 millimeters in depth. Okay, you can use flattened mills and a lot of stuff, but if I run the curvature here, this is 8.5 R. So I know that I can use a maximum diameter. I can use anything, but the minimum I need to use here is a 16 diameter. Imagine using a 16 diameter tool and trying to machine 108 millimeter depth. We are talking of an L by D ratio almost of 7. It's going to be catastrophic thing by trying to use such a long L by D and trying to cut this part. This is where 5-axis comes into play. And if you have a 5-axis machine, you should use the power of SolidCAM's functionality to take a 3-axis toolpath and convert it to 5-axis. So what I've done here is, if I unsuppress this toolpath here, I've done the rest roughing. Okay, I'll just show you what all has been done before that so that you get a gist of how this comes up. I first used a 50R3 bullnose to do the roughing of this part. Once this roughing has been done, I have then used a 16 cutter, 16 bullnose 1.9. It has got a short length, so it doesn't go everywhere. It has got a holder. So you can see that it stops here and then tries to machine some area here because the holder is coming into play, but it doesn't completely machine. So I still have got a lot of material remaining here. Okay. And to remove that very particular material, what I've done here is I have generated a rest roughing toolpath using 16 ball nose tool, but without using any holder. Okay. I didn't use any holder. And then I took this toolpath and used the same tool, but with a holder. So if you look at the toolpath that I've done, I have used 16 diameter ball nose, but with a holder, and the out of holder length is about 80 millimeters. So we're using an L by D here of about 5, which is acceptable. And how does this toolpath look like? So if I run the simulation in the machine, be very clear. What basically SolidCAM will do is it'll take the 3-axis toolpath, take the holder into account, take the geometry, and it will check for collisions with the holder and the geometry. The moment it finds collisions, it will tilt the tool automatically. Okay, so this is on a DMU 125 FD machine. Okay, 125P, sorry. And this is how my toolpath will run. So 3-axis. And as it goes down, I'll try and take you directly down below when it goes into the depth. It's already started moving, but I would like to stop at a particular point and show you the so when it comes close to the holder, you can see SolidCAM tilts this part. you can see the B and C values here. The BC values means that the toolpath is now a full 5-axis toolpath. It has already tilted, and it's avoiding the collisions against the holder with the taking into account the part geometry and the stock, obviously. Okay, and from a simple 3-axis roughing, I have now created a 5-axis roughing. So I can now use short tools and machine really deep geometries, provided you have got the holder to reach into that area. Okay, without worrying about the consequences, because that collision checking will be done by SolidCAM, and automatic tilting will be done by SolidCAM to reach into these deep areas. Okay, so this is how my toolpath looks like after it has been converted to 5-axis. So if I take an output of this is a hide and hunt control, and I can show you immediately the output. And if I run the toolpath, you can see that we are doing first 3-axis, and as we go down, we can start looking at the changes in the B and C angle. Okay, so it becomes a 5-axis toolpath. Wherever the holder is not going to have any collisions, the toolpath returns back to 5-axis. Wherever it is having collisions, it will automatically tilt the tool and to avoid the collision. Another very important thing, keeping in the same region, we have almost straight walls. So if I go into edit of this toolpath, and if I evaluate, do a draft angle analysis against this, you can see that this is having 0 draft. It's a straight wall. Now, if I want to finish this using an end mill, I would really need, again, a long end mill with an L by D ratio of 7, and it would create a disaster as far as the surface quality goes. So we have got the new generation tools, which are called as barrel tools, which offer the advantage of taking a very large step down, but giving you a very fine scallop. Now, to understand that, I will just close this tool, or let me start another instance of SolidWorks. I would like to show you quickly why you need to use barrel tools for such areas. Yes, please. Okay, sorry. Okay, so let me open the, I've made a simple sketch. So I would like to show you both. The tool I'm using here for barrel is a Amod tool. It's an oval form tool which has got 2 radiuses on its side. One is, if I again go back to the toolpath, and if I go into the tool library, if I show you the tool, this is how the tool looks like. I've got a tool with a very large radius. That radius is R80, and I've got a small radius at the tip, which is R2. So we use this big radius to generate or be in contact with the wall. And why we use this will be explained by the sketch here. So I've got 2 sketches here. One is assuming that we use the um, oval form tool with R80. So these are 2 circles. These are R80. And then I have got a smaller sketch here, which is the regular ball nose tool of diameter 16. Okay. Now the important thing is, if I edit the sketch, you see that I have got the step down and I have got the scallop value here. So this is the scallop value, the distance, the highest crest that forms, the mountain that forms when the tool takes a step over, that's scallop. At 1.5 millimeter step down, I get a scallop height, okay, of 0.003. You can see here where my mouse is, okay, because in SolidWorks, in my sketcher, I've put limitation of 2 decimals after the main digit integer. It is 0.00351. That is a scallop that it generates with R80 and 1.5 millimeter step down. So if I take with the oval form tool a step down of 1.5 millimeter, I will get 3 micron scallop on my wall. Now, if I want to achieve the same 3-micron scallop on my wall using a ball nose tool, okay, because if it is deep, then I have to use 5-axis and I need to tilt the tool. If I have to do the same thing using a ball nose tool, to generate the same 3-micron scallop, I would need to take a step down of 0.5 millimeter, which means my machining with a oval form tool is going to be at least 3 times faster as compared to a ball nose tool. So the functions that allow SolidCAM, so or rather SolidCAM has got functions inside its offering where it can generate toolpaths directly using oval form tools. Define your step down, pick the surfaces, calculate. Very important. So if you run the simulation, this is how it's going to look like with using an oval form tool. Just 1 millimeter downstep. In fact, I've not even used 1.5. I've just used 1 millimeter downstep. So I'm going to get even more finer scallop on that. The same thing is possible when you would like to do a surface below a flat area, but it's too deep. You can use what we call as a lens form tool to machine those areas. And this is how it will cut the area. Of course, I know that when this is being transmitted over the internet, it won't look like a continuous motion, but this is how the machining happens. I'll just go down here. Take this here. So the contact here is basically on the large radius. We are using the large radius, the R80 here, to generate the contact. Okay, very important. We are not using the front tip, which is just R2. I will not get the scallop using the front tip, but I'll get the scallop only when I use this large radius. So I have tilted the tool in such a way that I'm using the large scallop. If you look at the tilt value that's defined inside the software, I don't need to define any angle or anything. I just need to define what portion or what percentage of the barrel section should be in contact with the surface. The barrel section, very important. It doesn't consider the tip section, but it considers the barrel section in contact with the wall for machining. So if you take all the 3 paths that I just showed you, we calculated 2 paths right in front of you, and sorry, we calculate the paths right in front of you, and the summary is that SolidCAM can handle part of any size, any complexity. It can handle parts right from dies, molds, patterns, die casting dies, small dies, medium dies, large dies, machining with iMachining, machining with turbo, toolpath editing. You name the process, SolidCAM will offer that process for you to machine any kind of complex 3D geometry. When I say 3D geometry, I don't really restrict myself to only dies and molds. Any kind of 3D machining can be done using the 3D functionality, which is very, very powerful now inside SolidCAM. I believe that there are a lot of questions. I did try and answer quite a few of them when I was doing my webinar, but not every question will be answered by me. There is some question on how we know how to make the Excel sheet. Unfortunately, we do not have a straightforward tutorial, although there is a help available on how this can be done. I will try. I can't promise you, but I will try and make a tutorial on how, a video tutorial on how to create Excel based templates. We will try and take 2 templates and show you how this can be done. But you need to give me some time for that, because we really don't have it right now. I'll have to create it from scratch. Some person is asking about do you have any plans to support 5-axis roughing using bullnose? Well, for conversions, we do not have any plans to support tools other than ballnose from 3x to 5x, because I know the complexity that is there when you tilt a bullnose is very, very complex than when you tilt a ballnose. So ballnose tilting is way far easier and much smoother than tilting a bullnose. But right now, we do not have any plans. But if you really want to use 5-axis roughing using bullnose, then we have got 5-axis strategies inside SolidCAM that can address this area. Another very important thing that is coming up, and I think it's asked by William. Very important thing that is coming up in 2021 is automatic 3+2 roughing. The same part can be done, the same 5-axis roughing can be done using bullnose, but SolidCAM will identify how to tilt, where to tilt, and how much to tilt by itself. You do not have to specify anything. It will first generate a 3-axis toolpath. It will try to reach as much as possible. Areas that it cannot reach, it will automatically tilt the tool and try to reach into those areas. Even though if it can't reach those areas with that particular tilt, it will create another tilt within the same toolpath and try to reach into those areas. I think this is a very good answer for your question. Whether we can use bullnose, yes, it's coming, but it's coming in 2021. Somebody is asking if we send the links. Yes, the thank you emails that will go tomorrow to people who attended the webinar, also to those who missed it, will have a YouTube recording. You can view this webinar on YouTube. It's completely being recorded. It'll be available to you on your YouTube channel, on our YouTube channel, and the link will be there on your email by tomorrow. Somebody is asking that they work with very small tools, and can they work or can SolidCAM adapt to small tools? Well, yes, within our generic HSM. So if I add, let's say, a 3D HSM here, and if I go into machining, we have got an option called as micro milling. So you select a micro milling, and it will allow you to use very fine tools. It will adapt the toolpath tolerances and to the small geometry and the small tools, and generate toolpaths suitable for those small tools. So we do have micro milling facility available inside our generic 3-axis engine. I believe I have answered most of the questions. In event nothing is your question is still not answered, maybe I've missed because there were a lot of questions. In event you think that your question was not answered, or you would like to ask us a question, you can always email me on my email address, or you could, because whatever email that is going to go tomorrow will have the contact details, you could write to us on that. You could also download the latest version of SolidCAM 2020 SP3 and evaluate it for 30 days. For people who have SolidWorks, they can download the add-on. For people who don't have SolidWorks, we have got what we call as a complete CAD/CAM system, which includes SolidWorks for 30 days. You can evaluate the complete software. It's fully functional version. Once you evaluate, please get in touch with your local reseller or your local SolidCAM office, which can offer you training, because I do not advise you to directly start playing with the software without any formal training. Please get trained, start using the software, and we'll always get back to you with more informative webinars in the coming days. Thank you very much for patiently listening and looking at this webinar. I hope you liked it. I would love to hear from you on your comments on the emails that are going to go. You can write back to us. You can also tell us what kind of more information you need on SolidCAM for which we need to make webinars. Thank you very much, and have a nice week and a weekend. Bye-bye.